This is a lightsaber blade from Galaxy's Edge, and if we open it up, inside we will find a strip of RGB LEDs, and in the base of the blade a small PCB, which I am calling the blade controller. It is the job of the blade controller to receive commands from the lightsaber hilt and to control the LEDs based off of the command it received. So for example, if you have a Savvy's Workshop lightsaber hilt with a yellow kyber crystal in it, and you turn it on, this blade will receive the command to turn the LEDs on in the color yellow. Likewise, when you go to turn it off, it'll receive a command to turn the LEDs off, and it will do so. A couple of months ago, I did a video about this. This is my second attempt at creating a custom blade controller. The reason I wanted to create a custom blade controller is because Savvy's Workshop lightsaber hilts can recognize orange and cyan kyber crystals. They don't exist, but if you were to take an existing kyber crystal and reprogram it with the code for orange or cyan, the hilt will send the command to turn the blade on orange or cyan. The problem is the programming in the stock blade controller, instead of turning the blade orange, will turn it on as yellow. Instead of turning the blade on as cyan, it'll turn it on as blue. So that felt to me like a bit of missing functionality that I wanted to reintroduce into the blade. In the last video, I talked about some issues with this particular blade controller. It worked, it looks good, but the problem is the way it controls the LEDs. The LEDs in the blade are being turned on and off very quickly, and the ratio of how long the LED is on to how long it's off controls the brightness or intensity of that LED. So for example, if you wanted a strong red blade, you would turn the red LEDs on and leave them on 100% of the time. If you wanted an orange color, you would turn the red LEDs on 100% of the time, but then you would also turn the green LEDs on for about 50% of the time. So 100% red, 50% green, that will give you an orange blade. This technique of turning the LEDs on and off very rapidly is referred to as pulse width modulation. And the frequency at which the LEDs are being turned on and off by this, my second attempt at the custom blade controller, was too slow or too low of a frequency. The result was that you could, with your own eyes, you would look at the blade and it looked great. But if you took a picture of it or video of the blade, the camera, its sensor was fast enough that it could pick up that the LEDs were being turned on and off very rapidly. The end result is it created some artifacts in the image, usually as the form of a banding effect, where black bands would start running across the image, and if you're taking a video, the banding would appear to be scrolling up or down. It looked very weird. So if you were to take this somewhere and wanted to show it off, wanted to show your custom blade off to friends, and somebody tried to take a picture or a video of it, it would look distorted and not very good. So I wanted to find a new way of doing this custom blade controller that would allow me to generate that PWM signal at high enough frequency that cameras would be fine, wouldn't notice, or wouldn't generate that black banding effect. And that's where the previous video left off. In this video, I want to give an update about where things are with my custom blade controller and touch upon one particular issue that I ran into that should not have taken me as long to solve as it did. So let's take a look at where things are right now. This is the current version of my custom blade controller. And if we put it side by side with the one I showed in my previous video, we can do a little compare and contrast. The first thing is the microcontroller, so where the program that controls the blade lives. You can see that the new microcontroller is much smaller. It's also cheaper, and in my opinion, it's better suited to controlling the LEDs using PWM than the original microcontroller I was using, which was an ATmega 328P. The new microcontroller that I'm using is an ATtiny 1606. The voltage regulator for the LEDs has changed to something that's a little bit smaller as well. Again, trying to save some space on this board as it's pretty small to begin with. And the voltage regulator for the microcontroller has also shrunk a little bit as well. What's also nice is this particular microcontroller that I'm using now, or the voltage regulator for the microcontroller, has a much lower quiescent current, meaning if you leave this thing plugged in to your hilt, it only uses up a tiny amount of electricity. You could leave this blade plugged in with your lightsaber off and it wouldn't drain the batteries. It would take years for the batteries to drain. Whereas with this voltage regulator, it would not last as long. Other things worth pointing out here, we have our banks of transistors here, the same as the previous board. These are used to control the LEDs in the blade. And then we have a couple of electrolytic capacitors. They're there to help smooth out all the voltages that are on the board here. To help describe one of the problems that I came across, I think it's best to start with looking at the blade controller in this breadboard form. So here is the blade controller, here's the breadboard version of it, and we can see that they're almost identical. We have transistors up here on the left, the same as over here. Those are all transistors. We have a voltage regulator for the LEDs, that is right there. The voltage regulator for the microcontroller is tucked in right there. And the microcontroller itself is right over here. The boards that these chips are soldered to on the breadboard here are custom boards that I had to design because I didn't have anything that would allow me to take a microcontroller that small and plug it into a breadboard, or that voltage regulator and plug it into a breadboard. So I had to design them, get them manufactured, sent to me so I could put them on a breadboard and start testing this circuit. The one last thing that you might notice on this breadboard is over here on the right hand side. This is a USB to serial adapter. The main reason I have this here is it allows me to plug a USB wire into the breadboard here to power it. So I could take something like this, little USB charger, and plug a USB cable into it and use that to power the board. Another thing that I can use this for is I can plug this into my computer and I can use it to read any serial messages that I'm generating from the microcontroller. They're like debug messages, so every time the blade controller receives a command, I can send a message out to my computer so I can see what message or what command it thinks it received from the hilt. And whenever it does some special effect in the blade, I can have this send out a little message to my computer, and I can read it to make sure that the blade or the microcontroller is doing what it's supposed to be doing and try to debug any issues that come up along the way. So with all this laid out, I think the next step is to show this in action. Attached to this breadboard, I have a lightsaber blade. The blade controller has been removed, and I've attached wires to the strip of LEDs and brought them out here so I could connect them to my breadboard. Also coming off of the breadboard is this adapter. This allows me to plug the blade controller that's on the breadboard here into a lightsaber hilt. What's also kind of neat about that is the power connector for the blade goes directly to the batteries in the hilt. This means that I could plug my USB power source into the breadboard and I can actually power the hilt through the blade connector. So here is the battery pack for Savvy's Workshop lightsaber hilt, and I have no batteries in it. What I'm going to do is use this batteryless battery pack for my demonstration here. Here is my Savvy's Workshop hilt, and I'll just plug that in like so. The reason I'm putting the battery pack in at all is because the battery pack also houses the speaker. So all it takes now is for me to plug this in like so. I'll bring the blade over here so you can see that. I need a USB cable like this, and I'll just plug that in here. And then the other end, I'll plug into a battery charger like so. And we can see the hilt has power. We can see it's flashing a cyan color. That's because the red kyber crystal that's in here has been reprogrammed with the cyan code on it. So when I turn this on, it's going to send the ignite command for the cyan color to the blade controller. And if everything is hooked up and works right, and let's just make sure all these wires are pushed in because it'd look a little silly if it doesn't work when I do this. If everything goes to plan, this blade should turn on cyan. And here we go. And we have a cyan blade. To demonstrate the problem that I had encountered, I need to change the configuration of this circuit to match the design I had just before my latest version. Here we go. That's it. That's the change. Now when I turn it on, I'm not sure if it's going to come across on the microphone. I'll try bringing the microphone up to the speaker. Maybe you could hear that, maybe you couldn't. The problem is there was a high frequency noise coming out of the speaker. The problem is that whenever the LEDs turned on in the blade, there would be a sudden surge of current or electricity that was needed to turn the LEDs on. That sudden draw of current would cause a small voltage drop in the power rail throughout the blade and the chassis. Remember I talked about earlier how I can power the hilt, the chassis, through the blade connector here. The power is shared between the hilt and the blade, so any changes or anything that disrupts the power on the blade controller is also going to affect the hilt. So when this current draw suddenly happens, when the LEDs turn on, the voltage drops a little bit here at the blade controller, and it also drops a little bit here in the electronics inside the hilt. And it just so happens that the PWM frequency for the LEDs is about 10,000 hertz, or 10 kilohertz, and the frequency coming out of the speaker, which I've measured with an oscilloscope, is 10 kilohertz. The reason I have this capacitor over here on the output of the voltage regulator is because that's what I thought the original blade controller did. On the stock blade controller, there are two capacitors. The little one goes across the output of the voltage regulator for the microcontroller, which is sort of tucked right underneath this brown wire here, right next to that little capacitor. The output for the big capacitor, I figured, was across the output for the voltage regulator for the LEDs. It turns out that assumption was wrong. I don't know why I didn't do any kind of continuity checks to prove that before I started designing my own blade controller, but I got it wrong. I was lazy, I got it wrong. So my first few designs have the big capacitor going across the output of the voltage regulator for the LEDs. And because of that, the power that's coming into the blade, in other words, the power rail that's shared with the blade and the hilt, was seeing all these fluctuations. The fix, again, is pretty simple. Just bring the capacitor over to the main power rail, and it works fine, and I have no 10 kilohertz tone coming out of the speaker. What took me 2 months to sort of figure out, and I'm still not certain that I figured it out, is that there's a big difference between the breadboard version of the microcontroller and the fully assembled one. Each of these holes where you stick components into introduce a lot of resistance, more resistance than you would ever see when components are soldered to directly to the board. This increase in resistance, along with some other artifacts, inductance, and all of this stuff means that the behavior when it's on a breadboard is a bit different than the behavior when it's on the finished board. So the capacitance values that I thought would work based off of my breadboard use actually didn't work when I put them here on the completed board. And so I went through trying all sorts of different values of capacitors and capacitances, and I found that different types of capacitors with the same capacitance would behave differently or would diminish the ripple in the power rail differently. And rather than just sit here and try to talk to you for another 5 minutes, trying to make you believe in what I saw, why don't I just actually show you? Here is the breadboard blade controller hooked up to the oscilloscope. The trace you're seeing is the power rail here coming into the board. I'm going to remove the capacitor that we know fixes everything. I'm just going to move it over here for now. And now I'm going to turn the blade on. And we'll adjust this a little bit, and you can sort of see it's bouncing around a bit, but there is these big sort of saw blade looking spikes. I can stop it here, turn off the hilt, and we can really take a look here. And what we see here is the peaks and valleys of the power rail as the LEDs are being turned on and off. When the LEDs turn on, we see a valley because there's current draw on the power rail that brings the voltage down a little bit. When the LEDs turn off, the voltage rail spikes back up. If we look, we see about 50 millivolts per horizontal line or per division. So we're getting about 150 millivolts of ripple, which is what this change in voltage here is referred to as 150 millivolts of ripple on the power rail. So now I'm going to turn this back on. Actually, before I do that, I'm going to turn this on. I'm going to show you one other thing real quick. I'm going to zoom out a little bit in terms of time. And you're going to see that there's a bunch of extra stuff going on here, a bunch of extra frequencies sort of being picked up. The 60 hertz frequency of the electricity running through the wall is being picked up. The LED lights overhead, that's getting picked up as well. And there's a somewhat easier way to sort of filter all of this out. I've enabled the fast Fourier transform feature of this oscilloscope. It's essentially like a spectrum analyzer. It shows the different frequency components of the signal that it's receiving. Now, I'm going to turn this on, and I'm going to pause it, and then I'll turn it off so we don't have to listen to the noise of the lightsaber the whole time. So what you can see here is all the different frequencies that are incorporated into the signal or into the power rail here. And you see a lot of stuff at the lower end. A lot of that is, it can be noise coming from the speaker, stuff that's being picked up because the wires here that I have are maybe a little extra long and they're acting as antennas. But there's one very noticeable peak here, right over here. You see it's going off the charts there. And every vertical line represents 1.25 kilohertz of bandwidth. So that would be 2.5 kilohertz, 5 kilohertz, 7.5 kilohertz, and all the way up here, right where we see that big peak, is 10 kilohertz. That peak represents the ripple that's coming through on the power rail due to the LEDs being pulsed on and off very rapidly. So now what I'm going to do is I'm going to turn this back on, and I'm going to move the capacitor, which you can see way down at the bottom here. I'm going to move it from the LED voltage regulator output back to the power rail, and we'll just keep an eye here on what happens to that peak. You can see that peak drastically reduces, and the tone coming out of the base of the speaker, the lightsaber hilt, I can't even notice it. So that's all the problem was. It's just introducing capacitance to the power rail to prevent the ripple being generated by turning these LEDs on and off very rapidly, to prevent that ripple from getting back into the hilt. The question then becomes, how much capacitance? The stock lightsaber blade controller uses 220 microfarads of a capacitance. This one here is 820 microfarads of capacitance. And now we introduce my block of many capacitors, in which we discover that not all capacitors are the same. And this is what I've been doing for the last few months. I have spent more money than I care to admit buying different brands and different types of capacitors to try and figure this all out. So for example, this red one here, down on the bottom right, is also 220 microfarads. We're going to pull that out and use that in just a minute. And I have another 220 microfarad capacitor somewhere in here. I just need to find it. Here we go. Now, do I want to use that one? Why not? Let's use this one. This is another 220 microfarad capacitor. So what I'm going to do is actually pretty simple. Actually, first I'm going to put both of these on so that they're charged up. The reason being, if I put a capacitor that has no charge on it into the breadboard while everything is running, all the electricity gets sucked up into the capacitor until it's full up, and that leads to the microcontroller in the hilt resetting. So now, as the blade is plugged in, these capacitors are getting charged. Turning it on, and what I want to show you is, with just that red capacitor, we can see we've got a pretty good peak there. But notice, as I wiggle it in the socket of the breadboard, it changes a little bit. You see, this is the problem that I've been dealing with, is trying to figure out what I really need here. Now I'm going to remove that red capacitor and leave just the other one that's 220 microfarads. Same capacitance, same amount of electricity can be stored in both, but this one is a little bit better. Now, is it the socket? If I place the red one over here, is it better? Nope, I still get that big spike. If I bring this one and place it down here, does it get better? Nope, it's the same. But you can sort of see a combination of capacitors behaving differently because they're different. They're manufactured to different standards, along with the I don't know what the nice way to put it is, along with the unknowns of the contact point between the capacitor leads and the breadboard. Trying to figure out what capacitance I need and which capacitor I need has been a journey. And if you understood even a tenth of what I just tried to explain, you're probably better off than me at this point, because I have been staring at this, playing with this for months now, and I am slowly losing my mind. The point that I'm trying to get across is trying to identify causes and fixes or workarounds or solutions to the ripple problem in the blade controller are not as cut and dry as just throwing in a capacitor. Different capacitors behave differently. Where I put my probes, whether it's on my breadboard or it's on my completed circuit here, my completed PCB, will change what kind of ripple or how much ripple I see or how much ripple I measure. What I do know, though, is I made one of these and I put on it the larger 820 microfarad capacitor, even though I prefer to have a smaller capacitor. And with that 820 microfarad capacitor, it works. I don't notice the hum. I've tried hooking it up to the oscilloscope because it's possible that there's still a little bit of hum there and my ears just can't pick it up. But I think the hum is mostly gone. So why don't I just remove this and get a real blade? Here is a Galaxy's Edge lightsaber blade that I threw a gold sticker on. And if I open it up, inside you're going to see a strip of RGB LEDs. But instead of a stock blade controller, you have my new blade controller. So I'm going to put this together, plug it into the hilt, and we'll take a look at how it works. So I'm going to put in a battery pack with batteries into the hilt. And plug my custom blade controller powered blade into the hilt, like so. Maybe dim the light a little bit. Turn it on. And hey, it's a pulsing purple blade. But wait a minute, you have a cyan blade in there, a cyan crystal. What's going on? Well, I've been working on this for a while, and so I've got a bunch of different effects and different features, including the ability to store your last blade setting, which in this case was a slightly purpley blade that pulses like this, and I can turn it off or I can reset everything back to factory standard settings, I guess you could say, by just flipping this on and off a bunch of times in a row. And so we get into the software features of the blade. When the blade goes into reset, it clears out any saved settings and it disconnects itself from the hilt. So the hilt will make the noise of a blade being disconnected. That's how you know you've gone into reset mode. So you just keep turning it on and off very quickly until it goes into reset mode. So back into factory mode, I guess we'll call it. Cyan crystal, turn it on, and I get a cyan blade. Wonderful. But I've added other modes, as you have seen. How would you make it so that you could change the settings on a lightsaber when your only input method is the power switch? That's something that I've been trying to deal with for several months now, working on the code for this thing. And what I've decided to go with is how long the blade is kept off will determine if I change modes or not. So if I turn it on and then turn it off, and if I leave it off for more than about 3 seconds, turn it back on again, it's going to start up in the same mode as it was before. Your stock, whatever crystal you have plugged in, is what will appear on the blade. But if I only leave it on for about 500 milliseconds or so, I'm still getting a feel for what works best. It'll change display modes. So for example, if I turn it off and on again very rapidly, I am now in color picker mode. What this is going to do is it's going to cycle through a bunch of different colors, and when you see a color that you like, turn the lightsaber on and off again very quickly, and the lightsaber will remember that color and use just that color. So let's go with that purple color that I was using before. Not yet. Not yet. Is that it? I think I missed it. We'll go with pink instead then. So now it's stuck on pink. Now it's going to stay pink. And if I turn it off and wait a little bit, about 10 seconds or so, it will decide, okay, you really wanted to keep it on pink, and it will actually save the color pink to the microcontroller. So the next time you turn it on, you could unplug this blade, bring it to another hilt, plug it into that hilt, turn it on. It will remember pink. There are other modes that I've added as well. I'm not sure what's going to stay in the final code and what's going to go. I might add more stuff. This is still very much a work in progress. But here we have, it's cycling through the different colors, fading through the different colors, so you sort of have a blade that's generating all these different colors, just fading through them. Another mode, these are modes that you've seen before, where each segment has its own color, and it's sort of, the colors sort of flow down the length of the blade as they change. Now, if you look closely, you do see some slight banding. I couldn't fix that completely, but it's pretty close. It's enough that I'm not too worried about it. And then in this mode, each segment has a different color. And then again, one more on and off, less than 500 milliseconds, and it goes back to the first mode, which is the sort of stock kyber crystal mode. But I also wanted to add sort of sub-effects or effects to modes. So I might have just cycled through what I'm going to call different modes. And then each mode has what I'm going to call sub-modes. Or we could call them effects, mode effects. I don't know. I'm still working out what I want to call all of this stuff. So if you're in your stock mode, or if you're in the mode where you've picked a color, you can change what effect you see by powering the blade off and then turning it back on before 3 seconds. What I find works best is watch the blade animation, turn it back on after the blade is completely off. And now I'm into the first of several effects. This is an unstable mode which goes through the whole length of the blade. Every segment behaves the same way, and you can see it sort of flickers like this. The next display mode is similar, except each segment will flicker on its own, independent of the others. So you can see that there's a segment here and a segment here. The division is about right here. And you can see this flickers differently from this side. It does it down the whole length of the blade. But in this mode, what's happening is a pulse of light, or a pulse happens down here at the base of the blade, and then it propagates down to the end of the blade. So it looks like flashes of light flowing down the length of your blade. It's a pretty cool effect. This is a similar effect, except instead of a pulse or a flash of light, it's a darkening of the light, where the light suddenly goes out, and that sudden blackout travels all the way down the blade, and it's only a very brief blackout as it travels down the blade. It's a different way of presenting an unstable blade. Again, these are things that I just came up with as I was trying to come up with new ways to make the blade look interesting. And this one I'm definitely going to need a full blade shot to show you to really understand what's going on here. The base of the blade is flickering. The rest of the blade, the rest of the segments, will have the same brightness as this first segment, but some percentage of it. So maybe 80%, 60%, and 40%. So as this blade flickers, the rest of the blade sort of inherits some percentage of the brightness of the first segment. And it's an interesting effect. And then this is the last effect that I have right now. It's just a sort of a breathing effect where the light sort of fades out and then comes back. And then it pauses for a little bit and then it fades out again and comes back. Now I'm going to go on to other modes here. Now, the change, or the effect mode, if you want to call it that, for this sort of rainbow color changing system is it just increases the speed at which it cycles through the colors before it goes back to being slow. So now you can see it cycling through the colors much, much more quickly than it was before. And the same thing holds true for the where each segment has its own color, and the colors sort of fade or flow down the length of the blade. Turning it off for more than a second, but less than 3 seconds, and then turning it back on will again increase the speed, just like the rainbow effect you saw earlier. And then in this mode, this is where I'm at in my development, where I think more stuff needs to be fleshed out in this section. Every segment has a color, and what I'm going to do is, if I do that on-off again, it's going to step through right now what are a set of colors that I've predefined in the code. So it's going right now from red to orange It's very subtle in person. In the camera, I don't know if you can tell the difference at all. This one is orange to green, which reminds me of gummy worms for some reason. I've got a couple of colors I'm trying out here where it goes from a bright color to a dark color. The color's the same through the length of the blade, it's just different brightnesses in each segment. This is a green to white, and I'm sort of playing around with what looks interesting, and could I turn this into, instead of a lookup table of colors in the code, I could just generate the change in colors in code on the fly, so I save a little bit of space in my program. But does some color to white, is that an effect that is of interest to anyone? And the last couple here are just me trying different color transitions from one color to another, just to see what looks interesting. And we're back to the rocket popsicle mode. So that's the current state of my custom blade controller. I've gone through a few different designs over the last few months, and I've got one more that should be here within a week or so. Right now, I think the biggest thing that I need to work on is the code. It's something that I sort of ignored for the last few months because I was working on the hardware design. But once the hardware design was sort of figured out, once I felt comfortable with this version, and I had the one that's in the blade right now working and not creating that 10 kilohertz tone, once I got there and I felt comfortable, I started to really go back and look at the code, work on those effects to try and make them a little bit better. And now I'm just trying to figure out what else do I need to do or do I want to do with the code. So I am open to any and all suggestions about effects or ideas for the blade controller. One thing that I'm thinking about is, do I want to add a feature where you could set each separate segment a different color? So it'd be like that color picker feature where the blade cycles through a bunch of different colors. But instead, it's one segment at a time going through that same cycle of colors, and then it just keeps cycling through all the segments until you're happy, at which point it will, you would then power it off and then on again to sort of save the 4 colors that you set, and that would be your preset for sort of the 4 segments of different colors. And then maybe when you're in that mode with your preset of 4 colors, then you can loop through all those different visual effects, the blade fading in and out, the unstable effects and all of that. Or do I do a bunch of hard-coded presets like I already have right now and it just have it cycle through all those different presets and you pick the one you want? I don't know. This is stuff that I'm trying to figure out. So if you have any ideas or any suggestions or any feelings one way or the other, I am glad to entertain them. So that's about it. That's where things are. I'm hoping the next video I do about this is, okay, it's done. I feel comfortable. Here's where you can go download or order PCBs. Here's the list of components if you want to make one. Do a video where I assemble one of these and I show you how I assemble it. I haven't been posting much for the last couple of months because I've been trying to focus on this, and figuring out that capacitor issue has been more difficult than it should have been. Figuring out the code now is going to be my new time sink, so we'll see how it goes. I hope you found some of this interesting, and let me know what you think. I think it'll be cool. Well, I hope it'll be cool. We'll see.